All right, so today we're going to do geometric translations. Our key concepts are going to be what is a transformation, what is an isometry, and what is a translation. A transformation is anytime you move or change a figure. So we've seen some transformations already with the parabolas and with the basic shapes. When you move things left, right, up, down, when you reflect them over, when you rotate them, all of these types of things are types of transformations. We know you have a starting place. So let's pick parabolas just because they're fun. You have your 5 basic points for your basic shape, and then you transform it somehow, move it around so that it is somewhere else. The basic shape, the parent function, is the pre-image. It's where you're starting. And then you're moving that, and wherever you wind up, that final figure is called your image. So pre-image is just what you start with, image is what you end with. You are transforming the pre-image into the image. The points in the image come from the points in the pre-image. Translation is a particular type of transformation. It's just when we're shifting things right, left, up, or down. We're not changing its size, we're not changing its shape, we're not reflecting it, we're not rotating it. This is just left, right, up, down. So this is our warm-up today with mugwump, walking, and levitating. We noticed when we did our warm-up today that the lengths of the segments did not change, nor did the angles change. That is called an isometry. An isometry is a specific type of transformation. It preserves both length and angle measure. The lengths and the angle measures must be the same in both the pre-image and the image. You can't change size or shape to be an isometry. So those are our definitions. Knowing the definitions for most people is harder than actually doing the work. Doing the work, they give you a geometric picture. So now we're moving out of algebraic, can we graph that formula and move it around, to, oh look, they gave us a triangle. Can we then translate that triangle? Well, sure. If we're going to move point A, it says shift it 2 up and 3 right. So we're going to start at point A here. We're going to shift up 1, 2, and right 1, 2, 3. So here's our new point. We're going to do that with all 3 of the points. So we're going to take the point B and shift up 1, 2, and over 1, 2, 3. And we're going to take the point C and shift up 1, 2, and over 1, 2, 3. Each one of those points, where A goes, we're going to call A prime. We shifted the point 2, 2, up 2, and over 3 to get the point 5, 4. We shifted B, the point 5, 2, up 2 and right 3. And we shifted the point, oh, I forgot to put the B prime in there, sorry. C to the point C prime, up 2, right 3. So we are at the point 8, 6. And so there's our image. When we connect A prime, B prime, and C prime, that new triangle that we form is the image of the triangle ABC. The triangle ABC is the pre-image Notation-wise, we're going to use one type that's the same notation that we were using before. Our XY points, what are we doing to them all? We're shifting right 3, which is adding 3 to the X's, and up 2, which is adding 2 to the Y's. We can also say this is a translation, so capital T, and then subscript what we're shifting in the X and Y direction with the greater than less than sign bracketing them. That's going to say the same thing notation wise as take the XY points and shift them right 3 and up 2. Depending on what you're doing, it depends on which way you use your notation. Translating down and 1 left. So for me, I take these ones where they're trying to be tricky and saying the down part first and the XY part second, and I right away think of them as, okay, if I'm moving left 1, I'm subtracting 1 from the X. If I'm moving down 3, I'm subtracting 3 from the Y's. That's how I tend to think about it. So then I can move my points. So here's my new point A prime. There we go. Which is the point 1, -1 now. Which means B is going to be the point B prime, which is going to be 4, -1. And C is going to be the point C prime, 4, 1. So here's our new shape, our new image, A, B, C prime. And in our newer notation, we are translating this. We're subtracting 1 from the X's and subtracting 3 from the Y's. That's subscript on the T telling you to translate. So an isometry is a transformation that preserves both length and angle measure. The length and angle measure must be the same in the pre-image and the image. How can we tell if the lengths are the same in the pre-image and the image? One way is to use the distance formula. The distance formula between 2 points is the square root of the difference of the x's squared plus the difference of the y's squared. We should prove this formula at some point in this year so that you know exactly why it is the way it is. But right now, that's what the distance formula is. So, if the points are 2, 3, 3, 5, and 7, 1, and they're translated 4 units to the left and down 3, what are the points? Oh, I forgot an S. In the image. So, what are the points in the image? Well, we're taking our XY points and we're translating them 4 units to the left. Left means we're subtracting. So -4. And 3 units down. Down means we're subtracting. So A prime is going to be 2 minus 4 is -2, comma, 3 minus 3 is going to be 0. B prime, 3 minus 4 is -1. 5 minus 3 is 2. C prime, 7 minus 4 is 3. 1 minus 3 is -2. So there are the points for the image. So what are the lengths in between those points? So let's look at the length from A to B. These come as XY pairs. First an X and then a Y. We have two sets of them, so let's just call the first one X1, Y1, and the second one X2, Y2. Those subscripts are names for that X coordinate and Y coordinate, so that the different points have different names to them. Now we can plug into the formula that we have for the distance. So from A to B is the square root of x2 minus x1. When you take a negative and subtract, it's a plus. We're adding to that y2 minus y1. So we have 1 squared plus 2 squared. 1 plus 4. AB is the square root of 5. Switching to BC and running the formula again. We now have B and C as our 2 points xy's. So we want to call them something different. So x1, y1, and x2, y2 for the first point and the second point. The first x, the second x, the first y, the second y. And we're going to go plug into our formula. So the length from B to C is the square root of x2 minus x1 quantity squared plus y. I said x2, but I don't think I wrote down x2. So let's try that again. How about x2 minus x1? Actually picking up the x's this time. And y2 minus y1. Doesn't really matter what the order is you do those two in, but to be consistent. 3 plus 1 is 4. Negative 2 minus negative 2 is negative 4. So we have 16 plus 16, which is the square root of 32. 32 is the square root of 16 times 2, which is 4 root 2. And switching to the last set, what is the length from A to C? So our last 2 points, x1, y1, x2, y2, we're going to subtract the x's. 3 minus negative 2, quantity squared, plus negative 2 minus 0, quantity squared, which gets us 5 squared plus negative 2 squared, which is 25 plus 4, or the square root of 29. Some of us have probably realized at this point that I was using A prime, B prime, and C prime, the images. So what we have here are the images lengths, not the pre-images lengths. Luckily, that's not a big deal. Bam! Now they're the images lengths. So pause it, go through and find the pre-images lengths, and make sure that they're the same. So this time you'll be using those 3 points to find your lengths AB, BC, and AC, the distances between the point AB, BC, and AC, just like we did for the 3 points that we had over here. And then check to see if we get the same thing. So again, pause it. Do your own work, and then unpause it to see if you have what I'm going to get doing my work. Pause the video. So AB is the square root of 5. Its image is the square root of 5. BC is 4 root 2. Its image is 4 root 2. And AC is the square root of 29, and its image is the square root of 29. I did reduce the square root of 32 with the prime factorization method, broke it all the way down to its prime factors. There are 5 2's that could multiply together, each one of them underneath the square root. You compare 2 of them together, and get 4. The square root of 4 we know is 2. Multiplying the two 2's together, you still get 4 root 2. So it doesn't matter which methodology you choose, you're always going to get the same number when you reduce correctly. So this is good for our team. Are the corresponding lengths the same? The image A prime B prime corresponds to the pre-image AB. Yes, those lengths are the same. Same is true with B prime C prime and its pre-image BC. And same is true with A prime C prime and its pre-image AC. So yes. We're going to do a lot of work with triangles this semester. It's a big triangle semester, especially second quarter, once we get enough terminology and stuff built up to actually do good solid geometry work. It takes us pretty much all quarter just to build up our definitions and what we're doing enough to be able to even start with the triangles. So one really good thing about triangles is that if you can show that all the sides of one triangle are the same, they all have the corresponding sides have the same length, like what we just showed here, as all the sides of another triangle, then the angles formed by those sides are also the same measure. And so just by showing that these corresponding lengths are the same, we know the answer to the second part of the isometry question. The angles formed by those sides are the same. So that's really cool. We're technically using something that we don't know yet. You just have to trust me until we get there. In general, finding angles in the coordinate plane is pretty tough stuff. We will learn some of the basics in Unit 7, but how to do it for any angle anywhere in the coordinate plane is applicable until the end of pre-calculus trig, beginning of calculus. Like it's a tough problem just on how to find the angle anywhere in the coordinate plane given 3 points. So we're going to use some geometry tricks to not even worry about what the angles are and just be able to say, ah, yes, those two angles do have the same measure, with things like what we are talking about here. So there you go. That's an isometry. And we are at the end of our notes for the day. So this is very much like what we were already doing. It's a little simpler than that because we're just moving shapes left, right, up, or down. We're not reflecting or anything yet. We will be by the end of the week. So to make that a little harder, we also start working on our distance formula again. This distance formula isn't a new formula. It's the same distance formula that you've seen and used since probably 6th or 7th grade. Somewhere in there you wound up with the distance formula. Maybe 8th grade. I'll give you maybe 8th grade. But you wound up with the distance formula. You've seen it before. You saw it all through Algebra 1. They use the distance formula there. Didn't change. It's that same formula. You're going to use the same formula all the way through college. The distance formula doesn't change, and it's one of those things that you just want to memorize and be able to say, oh yeah, distance formula, there you go. When we get to the final at the very end of the year, and I say, no, you can't use a note card, and you say, but I still don't know the distance formula, and I say, I've asked you to memorize that since the 2nd week of school, don't look at me all shocked. I'm telling you right now, this will be on the formula. There will be a distance formula question. And no, you will not have that formula. You have to memorize this formula. So there you go. Have a great day.